everybody! Happy Monday! Thank you for joining me today. So, this is a little bit of a shock to the system. We've had a whole month of Summer of Nodes. I hope you enjoyed it. We had, for those of you who are, what's Summer of Nodes? We're going to do a write-up of this, so watch this space. But we had a whole month of August. We had loads of challenges, exploring lots of summer-themed activities, such as having a barbecue, such as visiting a museum, finding new places, exploration, that kind of thing. Even a murder mystery. We had a murder mystery as well. We had a lot of fun on those challenges. And as a result, we did pause these regular sessions on Twitch. So Mondays, I tend to have a look at an article from This Week in Neo4j, or if you suggest any topics to me on Twitter, so you can do, if you want me to have a look at something in the future, tweet me on Twitter. So normally I would have been doing that, but we paused all of that for Summer of Nodes. So we hope you enjoyed that and you took part in the challenges. If you didn't, don't worry, you can have a go at the challenges still. Those are all written up, so have a go in your own time. But we did a pause and now we are back to regular service. So I am back today and I am going to be looking at an article. Fun times. So, my dear, if you've got any questions whilst I'm going through things, please drop them in the chat if you're watching live. If not, you can put a message in our community forum, so that's community.neo4j.com. Send me a message on Twitter as well, or leave a comment in the video, we'll pick them up. So, what we're going to do this week? Yes, don't worry, so I've just saw a message in the chat about the Summer of Nodes. You can do it, so whilst there isn't a price to be grabbed, you can still take part. So do have a look and I'll post a link in for that at the end of this stream. Okay, so, right, what we're looking at today. Today, we are going to be having a look at Nathan Smith's recent blog post, which is looking at implementing Kmeans clustering with Cypher. So don't worry, if you're just going, what's Kmeans clustering? Don't worry, we'll do a quick run through of that, and Nathan covers that in his blog post. And we're going to go through that post. You've got a link to the blog post as well at the top of the video, so you can use that as well to have a look, and I will post it in the chat now as well. So you can have a look at that, and we're going to be going through that. And as I was going through this post, I thought, oh, you know what we could do, or we can have a go at? You've got a function within Cypher, within APOC, and what it allows you to do is to create like a custom defined function and procedure based on Cypher, and then you can keep calling it. And I thought, oh, I've got an idea. Why don't we have a go at that? So we're going to do the Kmeans clustering example, which Nathan provides in his blog post. And I thought, at the end, let's try wrapping that up into a custom function and then run it. Let's see what happens. So we can have a bit of fun with that. So this should be good. And let's get cracking. So if we go to the blog post, so again, you've got the link at the top of the window. And so what Kmeans is, I'm going to shoot down to the example here. So let me pick a picture. Let's scroll down to one of the pictures. It's probably easier to explain. So forget about the stars that you see on there. Don't worry about the stars. And if you think about it, you have some data, and you could have this data could be represented in a number of dimensions. And for those of you who watched a few weeks ago, we had an article which Dave Volter wrote about how he was looking at the graph embeddings, and he was looking at a paper where they used graph. They were effectively looking at using some graph embeddings that had some information coming back from how people were connected, and then they used K-means clustering to try and identify groupings of communities. So we touched on a little bit of that a few weeks ago. So we're now coming at the other angle where we're looking at K-means. And what K-means does, you have some data and you may have a number of dimensions for that data. And we've got a very simple example here where we've just got 2 dimensions. So let's say we've got our X dimension here and our Y dimension here. So we've got 2 dimensions, and bearing in mind we could have many dimensions, but we're keeping it very simple for today. We're just going to be focusing on 2 dimensions. So we've got this data, and again, ignore the stars. If we kind of look at this data, we go, well, we've plotted it, and if we look at this, you know, with our human eye, we can see that actually we have certain groupings. So we've got all of these data points, but we see that, you know, these data points seem to be forming into these sort of groups, these clusters. And it's like, well, we can spot them. Is there some kind of way that we can, in a, you know, sort of an iterative process, try to figure out, you know, where these clusters are? Because if you think about it, you know, they've got certain points. So here we have these groups that we think all belong to the same cluster, and we want to somehow tag that they all belong to the same cluster, and maybe there'll be some kind of a centre point there. Same with this one here too. We kind of go, oh, there's a grouping here, and maybe there's a centre point with all these things joined together. And what Kmeans does, and very clever. So K is means like the number of clusters we think we have. So with Kmeans, you have to say, well, I think there are n number of clusters here. So that's what the K means. So K is when we're saying we think there are K number of clusters. And means is effectively just referring to the mean average. And what's really, really clever about Kmeans, and I love this approach, is providing that we've got a good idea of how many clusters we think we've got, so how many Ks we're going to define. And what we do is we will randomly, and there's lots of different ways about how Kmeans can be initialised. So, you know, but bear with me. So we will say, well, we're going to randomly pick some starting points for each of these Ks. And then what we try to do is we'll have, so let's say, I don't know how many stars are here, but let's say we've got 15. We're saying we think we've got 15 clusters. So we're going to randomly pick 15 starting points for those clusters. And there's lots of different ways about, lots of different approaches you can initialise. I'm not going to cover that today. But we initialise our points. And then what we try to do is we go for each point and we try and figure out, well, based on the position of like the location we've given for one of our sort of like cluster location points, we're going to then compare each data point that we have, and we want to say, well, okay, so which point, you know, for each of our data points, which cluster does it best fit? And we're going to do that based on distance. So effectively we look at however many dimensions we have, and you know, we use good old Pythagoras here, where we look at the squares of deltas of differences for each thing, and we go, well, which one are we the closest to? And we do all of that, and we map that. And then what we do is when we've mapped all of the points based on which cluster position we think they belong to, we then go off and recalculate, based on all the points that we've allocated, we then recalculate where we think the central point of that cluster should be. And then we go through that process again. We try and figure out which point fits the medium. And it's really, really clever because we keep going this over and over again. And then hopefully, fingers crossed, because it doesn't always happen, but eventually we're going to get to the point where we go, well, this is the best point. So not only are we saying where our data points, which cluster our data points belong to, but we're also saying where is like the middle point of that cluster to. So where's the peak, for a better expression. And that's effectively what Kmeans is. So we go up here, we've got a bit of a description going on. So, you know, there's reasons why we would pick this. And I think example we've got here is, let's say, for example, we were collecting data for some volunteers. Yeah, so let's say we were collecting some data from volunteers. So let's say we had a load of volunteers and we were collecting their heights and their weights. So that could be 2 dimensions. So our X dimension could be the height of our volunteer, and the Y dimension could be the weight of our volunteer. And you think about that, and you sort of think about the groupings. And you're probably going to have some interesting groupings. You're going to have groupings based on, you know, people perhaps with a lower BMI and people with a higher BMI and those kinds of things. And you may want to form some clusters. So you're going to have some clusters of points based on those variables. And if you say, for example, I want to have three clusters, then you define your K as 3, and then you try to figure out where the median point, you know, where are the central points for these 3 clusters based on all of these data points for your participants, and you keep sort of iterating through getting the better and better fit. So that's effectively what Kmeans is. It's great fun. It has many applications. So if that's of interest to you, go have a look. Lots of fun. So that's roughly what Kmeans is. And what's really fun, this is a really fun blog post, because you probably don't want to use a database query language to calculate Kmeans for you, because it's not the most optimal tool. You can do it, but there are libraries that will do it much better, much faster. You'll have all of the various different point initialization approaches available. So you wouldn't do this in Cypher. But it is good fun with regards to understanding how Kmeans works, what it does. But also this is a great sort of mental gymnastics to start thinking about how Cypher works and what you can do with Cypher, and just decomposing a problem and thinking about how you'd solve it. So for that, it's really great fun. So you wouldn't necessarily, so we're not saying go away and do your Kmeans in Cypher, but this is good fun to think about A, what Kmeans is doing, and B, just practicing your Cypher prowess. So let's get cracking. So we talk about this, and then sort of Nathan gives you an example here, what is Kmeans, how it works, various links and that kind of thing. And let's have a look. So Nathan is using the sandbox for this, so I'm using desktop. You can do sandbox, it's totally fine. In fact, have a go, you can do this to anything. And sandbox is really great in that you can, you don't have to download anything, you don't have to install anything, you just go to the sandbox. And let me just pop a link into the chat. So you just go on there and you can have a play with Neo4j straight away. So if you want to have a go with this post, so again, links at the top, you can do that with the sandbox and join along with me if you like. So he's getting this running in sandbox, and he's doing the blank project for this, so the blank sandbox. We have APOC and all of that stuff in there, so you are good to go. And the dataset he's using here is from the University of East Finland with the clusters, so let's just keep running through this. And he's saying here we've got 5,000 data points, and they fall into 15 clusters. So Nathan here has provided us with the script to load that data, so let's go ahead and do that. Perfect. Okay, so that's all of that data is loaded. So, I've got an index there from a previous there, so I've not deleted the database. So ignore the animal bit. So we've got the data. So let's just do core db.schema. Okay, so we've just got items. So okay. So we don't have any relationships. So what we've got here is no relationships, we've just got data points, and that's fine. So for this example, we're just loading some data and having play with that. So we have got that data. Excuse me one moment. Okay, so we've got the data loaded, and we know there's 15 clusters here. So we've been told there's 15 clusters. So what we're going to do is we are going to create our centroid. So these are the things that we're initializing. These are things that we're going to be saying, these points belong to this centroid. So these are like our communities. So we're going to do those. So what's going on here? Let's have a quick look. We are matching our item nodes. And we are, so this, what's going on here? So let me just copy this query and I will talk through it with you in the browser. And again, if you've got any questions, fire away in the chat and we shall follow them through. So what's happening here is we talked about there's lots of different ways that you can initiate your Kmeans centroids. So your centroids, these are your clusters, your communities, whatever you want to call them, your Ks. And there's lots of different ways how you might go about initializing them. And one approach that you might use is you might say, well, actually, I'm just going to pick 15, because we're using a K of 15 clusters. I'm going to pick 15 random data points that I already have, and those are going to be my initialization points. And I'm not going to talk about local minima and maxima, that's out of the scope of this talk, but we hope, fingers crossed, that it doesn't matter which 15 points we pick, because we're going to keep iterating over and over and over as we try to find out which points best fit into that centroid, that even if we got it completely wrong and we picked 15 random things were 15 data points next to each other, hopefully, actually that's a terrible example, we hope that it's scattered enough so that even if it's not quite bang on, eventually it'll move into the correct place. It'll pick the correct mean and then associate those data points with it. So what's happening here, what Nathan is doing is he's picking 15 random points. So we're picking all of our 5,000 nodes. We're then with it, so carrying that on, the reference to that, we are going to pick random, sort order, and we're ordering by sort order. So effectively, we're picking 5,000 random numbers, and then we're going to sort that random list of numbers, and then we're going to limit it to the first 15 lowest random numbers. So that's our initialization point. And then we're now creating our centroid nodes, so there's going to be 15 of those. We are setting the location, so that's, that this is like the peak, we're saying, the center point of a cluster to the location. We're doing iteration, so come back to iterations in a second. So iteration is going to be how many times we run this algorithm, as it were, until we stop and return everything. So that's what's going on. So that's what we are doing, and this is just initialization, and there's lots of different ways we can initialize our centroids. But for the purposes of example, we're just picking random ones, and that is one approach that can be used. Right, let's run that. So that's going to go and create our centroids. There we go. So our 15 centroids and our 15 items. And then what happens next? And then we're going to give our centroids some numbers. Very good. So we could have done this in one query. That's fine. We can do it in two queries as well. So what we're doing here is we are collecting all of our centroids. So match with the centroids. We've got 15 of those. We are collecting them up into a list. We then want to create a list of 15 numbers. So range will give us an array of 15 numbers from 0 to 15. Give us a range of 15 numbers from 0 to 14. There, and we will 0 to 15 even as num, and then we're unwinding it, so now bring them as unique elements. And then what we're doing is we are setting the centroids, we're giving them a property name of cluster number, and it's going to be the number here, the unwind, and effectively we're just setting the numbers. So we will have centroids with numbers with a cluster number property between 1 and 15. So that's what's going on there. Let's go with that. All done. And what are we doing here? Okay, and then what's going on here is what Nathan has done is he's then returning this information and plotting it. So I'm going to skip this step, but obviously we're not going to have the same. So these stars, those are the centroids, but this is where we have sort of initialize them with that random number. So you can see they're in funny places. So that's what's going on there. So I'm not going to export this, but you can see what's going on. So it's roughly, this is what it's going to look like. Cool. And then what's really fun in this example, and there's lots of different ways you can do this, and maybe for a bit of fun, maybe in the future we can have a look at doing this. So what Nathan does to capture his points is he uses the spatial functionality within Cypher. And so here we have got 2 dimensions, x and y. So the spatial functions do cater for a third dimension, so for height. So you've got a z function as well. Z dimension as well. And what's going on here is he is using the distance function, because you think about it, you're using good old Pythagoras. That's what we do to work out the distances between where our centroid location is and where each other point is, and we're saying, you know, how far apart, what the distance is. And what we want to do is for each point we want to allocate it to the centroid that it's closest to, and Nathan does that by using the spatial functions in Cypher. So here what's going on, let's have a look at the query. I'm going to copy and paste this and then talk through it over here. And so what's going on here is that we're matching all of the items. We've got 5,000 items, and then we're matching all of the centroids. So that's 15 of those. And then what's going on is we're checking the distance between the item to the centroid, and then we're ordering it by the distance. So we're basically saying, find which items are closest to the centroid, so distance, and we're order by. So by default, if it's order by with no argument at the end, it orders in ascending order. So it'll be shortest distance to longest distance. And then what we're doing is we're collecting I, and we've got I, and then collecting the centroids because we've ordered them by smallest to largest. And then what we're doing is we're setting the cluster number, so the cluster, which cluster does that item belong to, based on the first item, first centroid in that list. So we only want the first one because that's going to be the shortest distance. So we're doing our allocations. This is where we're allocating starting clusters, points to their starting cluster positions. So let's do that. That should be relatively fast. Excellent. And then, so let's say we've done that. So next thing we need to do is we need to now recalculate the new position of the centroid positions. So remember we first time around we just randomly allocated them based on 15 existing item data points. Now what we're going to do is, because we've now allocated points that are closest to the centroid, now we're going to go for all of those points associated at centroid. We're now going to recalculate where is the better mean locate, where's the better location for that centroid. So let's grab this query here. So we're now going to adjust the centroid positions based on the points. So again, what we're doing here, so we're matching the items and the centroids. So we're basically joining, so we want to get all of the items that have got that centroid number, that cluster number. And then what we're doing here is we are taking the average of the X positions and the average of the Y positions, and we're then setting it as a point, setting the C locations. So we're setting the cluster locations. We're using all the spatial functions here. So point is one of the spatial functions within Cypher. And then we are saying we've increased the iteration. So now this is our next iteration. And the reason why we have iterations will become clear shortly. Okay, we do that bit. Perfect. And now we move on to... Yeah, so now we're going to move each item to the nearest centroid. So let's just step through this query. So again, matching item and centroids. We did this previously already, so we're now readjusting. We're readjusting the items onto new centroids. So we've already done this step before. So we step through this again. So again, we are ordering by distance. So which item is which centroid is closest to each item data point. So we're setting the various things. So doing this is all new. Same idea before. Again, we're moving the centroid again. So this is what's going on, and we're doing that iteration. So what we really want to do, we don't want to keep doing this to adjust it. What we ideally want to be doing is iterating this, because we want to keep iterating this because these things are going to keep moving, and we don't know how many iterations it's going to take. So what Nathan does here is he wraps it up into using a periodic commit. So let me just talk through it. So again, nothing here is new. The only difference is the function. So let me talk through what's going on here, and that iteration flag will all make sense. So this is all new. We've done this, so we know what's going on here. So the first thing we do is we map item to the closest centroid, and then we have the next part where we then update the centroid average based on the new, or the adjusted points that's being connected to that centroid. And we want to keep running that lots and lots of times until we have hit, we can iterate no more, or we can't always guarantee that this is going to have a finite number of iterations. It could be something where there's a point that's kind of on the border between two clusters and it keeps switching back and forth. But what we want to do is we either want to keep going to a sensible threshold, so maybe we want to specify some kind of a variance, or sort of number of standard deviations away from, for a point away from a centroid. Or what we can do is say, actually, we're going to run this iteration a number of finite times. And this is what Nathan does here. And what we've got is we've got all this stuff, so we recognise all of these things. But what we're doing is we're using apoc periodic commit. And what apoc periodic commit does is it will say, right, okay, run this Cypher query a specified number of times, and when it hits a certain feature, so keep doing this thing until you return 0, and when you return 0, then it stops running periodic commit. So you typically would see this function with, here's some Cypher with limit, $limit, and then here in these parentheses you'll have specified something like limit colon and some value, and this basically chunks out your query so that you don't, if you've especially got very large data, you don't pull the entire graph into memory to process. So this is if you're refactoring relationship names or something like that. So that's typically where you use it. So where Nathan is using this, which is really clever, is we're not specifying any parameters here because we've got this limit 1 because we want to run this with one limit and then keep going through. But what we do here, or what Nathan is doing here, is we've got these C iterations, and you remember we keep iterating this iterations, we keep upping it by 1 each time we go through this cycle. And what Nathan does here is put in a case when, and he's put this little catch. So as soon as C iterations goes over at 20, so as soon as it becomes 20 or higher, then we're going to spit out 0. So we're going to be returning 0, and that's the flag the apoc periodic commit is looking to be instructed to stop continuously running this Cypher query. So that's what's going on here. So here we're going to keep running it. So we've already done, I think, 2-3 iterations. So this is going to go for another 17, 18 iterations, and then it's going to stop. So let's run that. Oh, I bet. My apologies in advance. I suspect I have not installed apoc. So give me 2 moments. I'm going to fix that right now. I should have checked to see that I'd installed the plugin on there. So, I feel like I need a bit of lift music whilst I install the plugin and reboot. But so whilst that's going on, let's have a quick look. So I'm not going to go through, Nathan covers another example of a different sort of flavour of Kmeans. So I'm not going to do that. But you can kind of see what's going on here. So this is the idea of what happens when you're running that. And hopefully you see that and again, these may vary slightly depending on your start point. So I'm just wondering if this start point, oh, okay, it has moved. So you kind of get the idea of what's going on, how things are moving across, and you can see how we're moving, and we've used this combination of the spatial features to calculate the distances for us, as well as using apoc periodic commit to run this algorithm a number of iterations to move the clusters across. So you can get a flavour of what's going on there for about how we're calculating Kmeans. And what I'll do is I'll return a set of points per cluster. So we're not going to get this pretty visual. I don't have Excel up and running, but we'll have a quick look at the points that come back. So let me have a quick look. Are we good to go? Oh, we are. All right, perfect. So we should be able to run this now. So let's just let that just run. There we go. It's all executed. So now what we can do, I'm now going to return the points and clusters. So if we just quickly say what was our, so we've got cluster number, perfect, right. So let's do match C centroid. With C, I'm going to do, oh no, too soon, wrong button. Match item. Let's do cluster number is C.cluster number. So we're just matching the items to their associated cluster numbers. And what we could do, we could put a relationship between them, couldn't we? That'd be fun. We'll leave that for now. Let's do return C.cluster number. Collect. What properties did we have for item? So a quick look. Let's just do accounts. Let's do accounts. Count. I order by the cluster number. So you get an idea. So you can kind of see. So here are 15. Here are we've got our 15 cluster. Oh, we're missing one. No. Oh, okay. Not sure what's going on there. So we've got our clusters, and we can see here we've got like the number of clusters associated with that. So you've got a bit of fun there, and what we can do, let's order it by the count. So you can see here we've got like sort of cluster 12 has only got 106, whereas cluster 4's got 654 data points associated to it. So you can see there's a bit of fun going on there. So that's what's going on there. So what I wanted to do as well, so we've had a quick look at how we can use Cypher to do Kmeans. A good bit of fun. So it's a great way to have a play with the spatial, Cypher spatial. It's a good way to have a bit of fun with just working with Cypher. Have a play with the APOC periodic commit. So this was a good sample for this. And what I thought would be really fun to do now is we've got this big chunky this big chunky query here. So let's bring that one back up. And what I thought would be a bit of fun is, and I've not done this before, is can we wrap this up into a custom Cypher-based procedure? So let's do that. Okay. So this is what it is. So this is within APOC. So let me put a copy of the link in the chat. And what you can do is, let's have a look at the example here, is you can call APOC custom as procedure. And what you can do is you can give a name. So here, answer. And then you can give a query. What Cypher query do you want to do to execute when you run that query? And you've got the example here where we're going to call this procedure answer, and whenever you run answer, of course, fantastic tribute to Douglas Adam, we want to return 42 as the answer, because 42 is the answer to the life, universe and everything. For those of you who are a bit confused by this reference, check out Hitchhiker's Guide to the Galaxy. Fantastic book. So we've got this, and you've got an example, and here's an example of how we're calling this custom Cypher-based procedure. So call custom.answer, yield row, and it returns the answer. And we can also do things as functions as well. So I'm just going to have a quick look at this. So call as function. So let's to start off with, because I've never done this before. So let's have a quick look at the larger examples. And so I'm not necessarily going to run these. So we're probably going to run this as a function. But let's have a look at an example, and then let's go crazy and have a go at implementing the Kmeans stuff as a function. I don't know if it's going to work or not. I've not done this before, but it's all good fun. Alright, so what we want to do is, Okay, so we can use parameter to do the parameters. Oh, this is very difficult to read, but that's as in because my resolution's very low, so I do apologise for that. But let's. Okay, so let's have a little play with the example we've got here. So we've got it as function. So let's do this. Let's have a go with this. Let's see what happens. Right. Okay, so this is creating it as procedure. I want to do this as a function, I think. Alright, so let's see what happens. So let's do as function. Okay, so let's create our function. So when we want to call it, let's see, what was the example? Let's see what happens. Oh. I was not expecting that. I'm just going to make this a little bit bigger because I think it's make it a bit easier to read. Sorry about this. This is literally, I just thought I'd have a go at this because I thought it'd be a bit of fun. Aha, so okay, that's how we do the input. So if you're feeling really clever, we could do this to initialize it, but I'm not feeling that brave. So let's. May have to abandon ship on this and have a go offline. Obviously. How do I call custom? Hang on. As procedure. Okay, right, that's where I went wrong. So if we now do the... This will return 42. No, oh no. Oh. not sure what's gone wrong. Let's copy and paste it one more time. If it doesn't work, then I will have a play offline and then I will follow up and tell you how I got on. I've done this. I'm just going to copy and paste. Oh, because I need to return row.answer. No. Okay. I'm going to park that there. I need to go off and have a look what's going on. So I will be back with an example that works. But anyway, back to topic. So I was going to wrap it in. So I will have a go and I'll come back to having a go at wrapping this up. Because what we're going to do is take this, it's a bit of fun, and just wrap it up and just wrap it into a Cypher-based procedure using the APOC procedure. So I'll have a go at that and I'll report back. But anyway, so that's Nathan's blog post. So he does go on and talk about using Kmeans++. So do go and have a look at the blog post. So hopefully this has got you really excited about Kmeans. So again, you've got the address to the blog post at the top there, top of the video frame. So do have a look. Do have a play. You can do this in Sandbox. You don't need to download anything and have fun. So as a quick reminder, my colleagues, as always, are back doing various streams as well on different topics. So Adam is on Tuesdays, Michael will be on Wednesdays, Will is on Thursdays, and I will be back on Friday for another episode of Adventures with the Wine dataset. I'm really excited. I've been missing that dataset, so do come and join me. I'm going to update the repo very soon, and then we're going to be doing some more work tackling the descriptions. So I hope you have a fantastic day, and I will catch up with you next week.